Is given the next information. This question asks you to explore properties of a family of curves of the type y squared is x cubed plus ax plus b for various values of a and b where a and b are natural numbers. A. On the same set of axes, sketch the following curves for x is in between -2 and 2 and y is in between -2 and 2, clearly indicating any points of intersection with the coordinate axis. AI. Y squared is x cubed for x is greater or equal than 0, 2 marks, and AII, y squared is x cubed plus 1 for x is greater or equal than -1, 2 marks. Since y squared is, we can write that y is plus minus x to the power 1.5, and for the second, y is plus minus square root of x cubed plus 1. Plus means a curve is above x-axis, minus means it's below x-axis, and these curves will be symmetrical about x-axis, and we can use calculator, and we set y is x to the power 1.5 and y is negative x to the power 1.5, and the second curve y is x cubed plus 1 to the power over half, and also the same with minus. Window x, y are in between -2 and 2 as required, and the required graphs looks like this. Y squared is x cubed, it's this curve. We can see that when x is 0, y is 0, so 0, 0 must be present, and it looks a bit shifted, but this sharp must be at the origin. So this curve is y squared is x cubed, and this curve is y squared is x cubed plus 1, and we can see that when x is -1, y is 0, it's x-intercept, and when x is 0, y is 1, so 0, 1 is y-intercept, and also 0, -1 is also y-intercept. The next, BI. Write down the coordinates of the 2 points of inflection on the curve y squared is x cubed plus 1, 1 mark. Since there is only 1 mark, we should deduce it from a graph. We should consider this curve, and we can see that a point of inflection is at 0, 1 and 0, -1, because we can see that to the left it is concave down, to the right concave up, hence at 0, 1 and 0, -1 it changes its concavity. Definitely we can find a point of inflection if we consider the second derivative and equate it to 0, but since there is only 1 mark, we should deduce it directly from the graph. So 0, 1 and 0, -1 are points of inflection. BI, BII. By considering each curve from part A, identify 2 key features that would distinguish one curve from the other, 1 mark. And we can see that y squared is x cubed has a sharp, the other does not. Y squared is x cubed plus 1 has points of inflection, the other does not. The next. Now consider curves of the form y squared is x cubed plus b for x is greater or equal than negative cubed root of b, and b is positive integer. C. By varying the values of b, suggest two key features common for these curves. It means that if we consider here b to be in general instead of 1, we can deduce that we will get absolutely the same curve, but coordinates of these and these points will be different in terms of b, and you can deduce that x-intercept will be negative cubed root of b, and y-intercept it will be, when x is 0, y is square root of b, but plus minus square root of b, but shape of this curve will remain the same. So we can say, and we need only two features, so we can say the next: when x tends to infinity, y tends to plus minus infinity, or same range, because range remains the same from negative infinity to positive infinity, plus infinity, or same line of symmetry, y is 0, or one x-intercept or two y-intercept points. Or actually it's enough, but also it's possible to say that same x-intercept in terms of b and same y-intercept in terms of b. Only two required. The next. Now consider the curve y squared is x cubed plus x is greater or equal than 0, and di shows that dy dx is for x is greater than 0, 3 marks. So we need to just find the derivative dy dx. And since we can see y squared, we should apply implicit differentiation. So we differentiate both sides with respect to x, and derivative of y squared, it becomes 2y dy dx is equal to 3x squared plus 1. Hence dy dx is 3x squared plus 1 divided by 2y, and y is plus minus square root of x cubed plus x, plus minus square root x cubed plus x, and it is equal the expression as required. dii. Hence deduce that the curve y squared is x cubed plus x has no local minimum or maximum points. 1 mark. To have maximum or minimum, the first derivative should be 0, and let's consider derivative to be 0. So fraction is equal to 0 and numerator is equal to 0, and we can see that x squared is negative 1/3, but x is greater than 0, so no points where derivative is equal to 0. Or we can write that dy dx cannot be equal to 0, hence there are no maxima or minima. The curve y squared is x cubed plus x has 2 points of inflection. Due to the symmetry of the curve, these points have the same x coordinate. Find the value of this x coordinate given your answer in the form, and form is given. 7 marks. So we need to find points of inflection, and we know to be a point of inflection second derivative should be equal to 0, so we consider the second derivative and then equate it to 0. So consider second derivative, and we can see that there is division, so applying quotient rule it becomes denominator squared and numerator derivative, it's 6x multiplied by the denominator 2 square root of x cubed plus x minus numerator 3x squared plus 1 multiplied by the derivative of the denominator, so it's 2, it's just constant square root derivative, so it's a function to the power of a half, and applying chain rule it becomes half x cubed plus x to the power of negative a half, or divided by square root of x cubed plus x, and according to the chain rule multiplied by x cubed plus x derivative, which is 3x squared plus 1. 2 cancels here, and it should be equal to 0 to find the point of inflection, and we consider numerator to be equal to 0, and it becomes, and we can make a common denominator of this numerator, and it will be square root of x cubed plus x, so it becomes 12x, and square root multiplied by square root it becomes just x cubed plus x minus 3x squared plus 1 multiplied by 3x squared plus 1, or just squared, is equal to 0. And again, fraction is equal to 0 when numerator is equal to 0, so it becomes 12x to the power of 4 plus 12x squared minus 9x to the power of 4 minus 6x to the power of 2 minus 1 is equal to 0. And it becomes 3x to the power of 4 plus 6x squared minus 1 is equal to 0. To solve it, we can denote x squared to be t, and it becomes 3t squared plus 6t minus 1 is equal to 0, and using discriminant becomes b squared 36 minus 4ac. So it's 48. Hence xt, and t is x squared, so x squared is equal to minus b plus minus root 48 over 8 over 6, and it becomes root 48, it's 16 over 3, so 4 root 3 over 6, so negative 1 plus minus 2 root 3 over 3, but x squared must be positive, so it means there will be a root only when it's positive, so they can take out only 2 root 3 over 3 minus 1, and hence x is again plus minus square root, but it is given that x is positive, so x will be positive square root of 2 root 3 over 3 minus 1, and it is given the required form. It looks like x is square root of p root 3 plus q over r. So we do a common denominator, 2 root 3 minus 3. Yes, it's correct. It's as required. The next, P, point P with coordinates x, y, is defined to be a rational point on a curve if x and y are rational numbers. Rational, it means can be written as a fraction. The tangent to the curve y squared is x cubed plus ax plus b at a rational point P intersects the curve at another rational point Q. Tangent to the curve at P intersects the curve at another point Q. Okay, let C, it means curve, be the curve, y squared is x cubed plus 2, for x is greater or equal than negative cubed root of 2. The rational point P with coordinates negative 1, negative 1 lies on C. Fi. Find the equation of the tangent to C at P. Tangent to the curve at P. 2 marks. So to find tangent to the curve, or actually we know that we need gradient firstly, and to find gradient we need differentiate, and equation of a tangent we use y is mx plus c, or of the form y is y1 is gradient x minus x1, where x1 y1 is point negative 1. We substitute a point negative 1 as usual. So to find gradient we need derivative. So let's differentiate again. 2y dy dx is 3x squared, hence dy dx is 3x squared over 2y, and y is plus minus in general square root of x cubed plus 2, and it's actually this curve, but a 2 instead of 1, and it will be the same, but another xy intercepts. So let's draw it. It looks like this, and we can see that when x is 0 it's square root of 2, and it's minus cubed root of 2, and root 2 it's 1.4, and negative 1 it's somewhere here. Oh, no, it's not here. It's negative 1 it's here. Negative 1 p negative 1, and we can see that tangent is decreasing line here, so we should take minus. So derivative dy dx at -1, or at point P, is minus 3/2, and substitute -1 for x, -1 squared, square root -1 cubed plus 2. So it's 1, it's minus 3/2. Hence, equation of a tangent becomes y minus -1, so plus 1, -3/2, x minus -1, x plus 1. It's the required tangent to the curve at point P. Hence, find the coordinates of the rational point Q where this tangent intersect the curve, expressing each coordinate as a fraction. 2 marks. So it looks like this. There is tangent at P and it intersects a curve at another point at point Q, and we can see that this point is somewhere here, and we need to find point of intersection of two curves. The first curve is our tangent, and we can rewrite as -3/2 x minus 3/2 minus 1 or minus 5/2, and another, it's our curve, and it's what, y squared is x cubed plus 1, but since it's below x-axis it's minus, it's y is minus square root of x cubed plus 2, and we need a point of intersection. We can find it with a calculator. You should consider this is equal to this and find the point of intersection, or move it to the left and consider minus 3/2x minus 5/2 plus root x squared plus 2 is equal to 0, and plot only one graph and find x-intercept. For this, you should plot two graphs, the left-hand side, the right-hand side, and find a point of intersection. But if you move everything to one side and equate it to 0, you need to plot only one graph and equate it and find x-intercept or 0 over function of this function. And if you do that, you get that x is 17/4, and substituting x into either into this or this, it doesn't matter, you get that y is -71/8. Hence q has coordinates 17/4, -71/8. And the last question, 5 marks. The point S with coordinates -1, 1 also lies on the curve. The line QS intersects curve at a further point. Determine the coordinates of this point. So it is given another point S with coordinates -1 and 1, and we need line QS QS, and this QS intersects a curve at further point, so we need this point. Coordinates of this point, let it be, for example, K. So we need to find for coordinate of a point K. So, and it is given coordinates of S, -1 and 1. And how to find the point of intersection? And actually, point of intersection of what? It's of the line QS through Q and S, and again a curve, this curve. So we need to find the equation of a line through 2 points. It's quite easy as usual to find the equation of a line. Use again formula mx plus c, or y minus y1 is mx minus x1. For x1, y1 we can use any point on the line, so it will be more easier. Use -1, 1, so it becomes y minus 1 is m gradient x minus -1 plus 1, and we need to find gradient. To find gradient rise over on y2 minus y1, x2 minus x1, so it becomes -71 over 8 minus 1, and for x 17 over 4 minus -1, and it should be 79 over 42. Hence equation of a line becomes y minus 1 is 79 over 42, x plus 1, or y is 79 over 42, x plus 1, and again we need point of intersection with the curve y is negative square root of x cubed plus 2, and again plot a graph and find the required point of intersection directly from the calculator. So again, you may plot 2 graphs and find the point of intersection, or you may move it to the left and consider 79 and consider only and plot only one graph plus equated to 0. So plot this graph and find 0. Find 0. And the answer must be the next. X is 0.288 to 3 significant figures, and the required point has the next coordinates 0.288, -1.42. To find y, you substitute x into this or this, because it's a common point. So it was the point S with coordinates, it was G, the point S with coordinates -1, 1 also lies on C. The line QS intersects a curve at the further point. K here determines the coordinates of this point. Yes, so it's the required coordinates of the point. And that's all for this question.